All right, in this segment, we'll start looking at the main function in the template file, and that's a symbol system. All right, so let's move over and look at the code for a second. Here a symbol system is only called once, of course, and so here we zero out k and f. I've defined several constants and objects up here. So I don't think I've used this before. I have const unsigned int. And so what that constant does is it allows me to define this variable only once. So it's actually not even a variable. It can't vary. It's a constant. So this DOFs per element is degrees of freedom per element. And then, of course, that changes with your basis function order. All right, same as number of nodes per element in our case. Then I declare what a full matrix. Again, this is another DL2 object, and it stores doubles. And as I'm initializing it here, klocal is DOFs per element by DOFs per element. Okay, it just defines the size of the matrix. Again, flocal is also a DL2 vector with length DOFs per element or nodes per element. Now here I'm creating this standard vector of unsigned ints called local DOF indices. It also has a length of DOFs per element. And this vector we will actually update for each element. It's different, the values in it will be different for each element. But what it does is it relates our local node numbering to the global node numbering. Okay, so let's look at that for a minute. Again, I'll create another sample domain. I'll do, I guess in this case, 3 elements for quadratics. So we have one midside node. And let me do the global node numbering on top. And then on bottom, I'll do the local or the element node numbering. Again, both of these are in DL2's syntax. All right, so we have 0, 1, 2, 3, 4, 5, and 6. Okay, and now I'll break this up into element 1. Let's call it E1, E2, and E3. Okay, so those are our 3 elements. So locally, these nodes would be labeled 0, 1, 2. Same for all of them, 0, 1, 2, and 0, 1, 2. Okay, so local DOF indices will look different for each element. So local DOF indices. For element 1, this is what it will look like. Global node 0 corresponds, or local node 0 corresponds to global node 0. Local node 1 corresponds to global node 1. Local node 2 corresponds to global node 2. Okay, so they all match up there. And let me specify here that these are the global nodes, or local nodes. All right, let me change that. So on the top, this is the index, is the local node, and the actual value stored is the global. So the index is local, and the value is the global node. Okay, so for E2, again, we have 0, 1, 2. But globally now, we look at element 2, local node 0 corresponds to global node 1. Local node 1 corresponds to global node 3. Local node 2 corresponds to global node 4. Now, of course, DL2 is handling all of this for us. It will populate this local DOF indices vector. But I just want you to understand exactly what's going on here. So for element 3, Now we look at local node 0 here, corresponds to global node 3. Local node 1 is global node 5. Local node 2 is global node 6. So if let's say we're working with element 2. We've initialized local DOF indices for element 2. And so now using the C++ syntax, if I put in 1 as my index, it would give me 3. Right? If I put in a local node of 0, it would return 1, a global node number of 1. Okay? So this vector local DOF indices will relate our local node number to the global node number. The index to the vector is the local node number. The value stored is the global node number. All right? And we'll need that especially when we're going to assembly. Okay? So now let's go, let's see, I also have these variables stored here. They're all doubles. HE is the element length. X we'll use to find the value of x at quadrature points, which we'll need to define our forcing function. And then F is the value of that forcing function. Okay, now we have a loop over elements. Now this is where, remember in our review of C++, or introduction to C++, we talked about iterators. And they're similar to pointers in some ways. Okay, and that we use these that we can use iterators in for loops. Okay, so in this loop over elements, we're actually using an iterator. You can see here it's an active cell iterator. By the way, in the DL2 name nomenclature, they call elements cells. So when you're seeing a name that DL2's set up, it usually says cell for the element. Okay, so here we're actually looping over elements. They're called cells. All right. And now all of this, I could have put, this line, elem equals DOF handler dot begin active. I could have put here in this declaration portion of the for loop, but since it's so long, I can declare it ahead of time, and that's okay to have an empty spot there in the for loop declaration. All right. Okay, so I've declared two objects here. I have elem, which is my iterator, and I'm setting it to the beginning element. I also have this end C, which is the last element, or really it's a marker after the last element, okay? And so in my for loop, I'm already starting at element equals the first iterator, or the iterator is equal to the first element. And my condition is as long as I'm not at that marker past the last element, then I'll go through the for loop. And again, this plus plus elem, it just increments to the next element. Again, even though elem is not an integer, it's an iterator, the plus plus still iterates forward. Okay? So now that we're within a particular element, we have to update the local DOF indices vector. Okay? So we do it this way, elem arrow get DOF indices. Remember, this arrow is the way we, for either a pointer or in this case an iterator, this is how we access a function. Okay, so since elem is an iterator, instead of doing elem dot get DOF indices, we have to use this this arrow essentially. Okay, and so that will populate the correct local DOF indices with the correct global node numbers. Okay. All right, now I'm going to find for you the element length. As I told you before, in the way we've defined our mesh, each element will have the same element length. So you could actually have just taken the length of the whole domain and divided by the number of elements to get element length. This is just a little bit more general in case you ever set up your mesh to have elements of different lengths. What we're doing here is I'm saying HE is equal to the node location at local node I minus the node location at local node 0. Okay, remember local node 1. So local node 1 again is always on the right can look back here on our schematic here. The local node 1 is always on the right of the node. Local node 0 is always on the left. If we take the x coordinates of those two and subtract them, then that gives us the element length for whatever element we happen to be in. Again, I use local DOF indices, though, because I may not be in element 1, I may be in element 2. And I really want and remember, node location, the vector node location is indexed according to the global index. And so I would want, in this case, if I wanted the x values at local node 1 and 0, I would need the global node numbers 3 and 1 in order to access the correct x values within my node location vector, right? So that local DOF indices will come up again, as will node location. All right, but now we have HE, which is our element length. Now, first, let's create our local force vector, F local. Now, there are really two parts to this, right? There is the portion due to the forcing function, or the body force. And then, if you have a Neumann condition, a non-zero Neumann condition, like we do on problem 2, then you'll have to add in the effect of the traction at that boundary, okay? So first, we will do the portion of F local due to the body force. Okay, so here I've set F local equal to 0. Again, that we zero it out for each new element. And now I'm looping over A, so each component of F local, right? So I'm at F local component A, and now I'm looping over my quadrature rule. Okay, I'm looping over each quadrature point, because we will need, remember, in F local and K local, we're performing integrals. All right, so let me actually write out this general form for this portion of F local. Again, this is in the lectures, but let me write this out. So F local component A is equal to the area, the cross-sectional area, times the element length over 2. Remember, we use that element length over 2 to convert from by unit domain to the real domain. We're integrating from -1 to 1. Basis function A corresponds to our index here, evaluated at nodes C, times our forcing function, or our body force F. F we're given as a function of x, but since we're integrating over C, we need to evaluate everything in terms of C. Okay? And then we integrate it over our dxc domain. Okay? Now, since we're using quadrature, let me write this out using quadrature points. AHE over 2 is still on the outside. However, now we're going to loop over our quadrature points. And so I'll just do Q equals 0 as long as we're less than quad rule. Okay, and now we're going to evaluate the integrand at each quadrature point. And remember, you get the quadrature point from that quad points vector. I'm going to distinguish it here just by saying it's CQ. So CQ is the quadrature point. Okay. Then F is a function of x, but again, we can get x, the value of x for that particular quadrature point. Okay, now it's no longer an integral, it's a summation, and so we also multiply by the weight. So that's short for the quadrature weight at that particular quadrature point. Okay, and again, that's also it. We also have a vector of quad weights. All right. Now, this term should be easy enough to evaluate because we already have our basis function that has as an input the node and xi. Now here, you're given a forcing function or a body force. How do we do this term here? we have a value of xi, we need a value of x. So this is also something from the lecture, but just as a reminder, we can interpolate over the values of x at our local nodes to find the values of x at xi. So let me specify here that this is the value of x at xi q, for example. Okay, so what will we do? We'll start at a equals 0, and as long as a is less than the number of nodes in the element, we will take x a times our basis function evaluated at xq. And what do I mean by xa? This is the value of x at node A. In other words, which we can get from node locations, okay? Node locations, but remember, A is a local element, or a local node number. Node locations requires a global node number, and so to convert, we use this local DOF indices of node A. Okay? Now I've actually written all of this up for you in the code, but I wanted to explain it to you in this one case because you will be performing other integrals in this homework and another homework assignment, so I want you to understand what's going on here. Okay? So going back to the code, you can see, again, we're looping over b equals 0, b less than DOFs per element, or in other words, less than number of nodes in the element, and x plus equals, so we're doing this summation, node location at local DOF indices b times the basis function of b quad points q. Okay? Again, I'm just using the index b instead of a, but it's the same thing, right? Okay, so now you have the value of x here. This is where you have to start doing it yourself. So now that you have x, you'll need to evaluate f, evaluate NA, and essentially just create this integrand. Well, what was an integrand and is now this inner portion of the summation. And you will use that to define f local at A. Okay? So you'll need to do that. Now that takes care of the body force. However, in problem 2, or part 2 of this homework, you also have a Neumann condition. Of course, that only applies at the right-hand node. And so what I've done here is if we're at problem 2, then it's checking if your node location, if the node that you're at is on the right-hand side, then that's where you'll have to add in the attraction times the area, which is h. Okay, so you're really just adding in h to the appropriate component of f local. And again, you can review your lectures if that process is a little bit fuzzy. Okay, so that will take care of your f local. So we've taken care of the body force, and when applicable, we've taken care of the Neumann boundary condition. Now the next part is to define k local. And let me write out the general form for k local as well. Now k local is, of course, a matrix. So let's look at component A, B of k local. We have 2EA, E is the Young's modulus, A is the cross-sectional area, over HE, where HE is the element length again. And here we've already converted to an integral over the bi-unit domain. That's why we have the HE in there. Now we're dealing with gradients. So this is the partial, I guess the derivative of basis function A with respect to C times the derivative of basis function B with respect to C. Okay? And so again, these two terms you will get from your basis gradient functions that we've defined previously. All right? And again, Here you'll convert this integral into a summation over quadrature points multiplied by the appropriate quadrature weight. Okay, so I've set up the for loops for you. We have a loop over A and a loop over B and a loop over your quadrature points. Now you simply have to write out what is k local AB equal to. And of course, since it's a summation, you'll be doing a plus equal just like you did with f local and like we did with when evaluating the value of x at the quadrature point. Right? Okay, so once you've filled in those lines, you'll have your f local and you'll have your k local. Okay, f local will already have any Neumann boundary conditions that are involved in the problem. Now you need to go to assemble system. You have to actually assemble them into the global matrix and the global force vector. Now again, this was done in the lectures. You can go back and review that there. The real trick of it here is to remember to use local DOF indices, and it makes everything very simple. So, for example, if for f, we have the global node number. So essentially you'll, for each element, you'll be looping over the nodes, each node in each element, okay? And you'll put that value of f local into the corresponding value. That should be a plus equals, because we don't want to delete any values that were already in f, right? We just want to add on to them. And so you add on the f local for the local node number. Okay, and the local node number will of course be going from 0 up to the number of the nodes in the element. And then how do you go from the local node number to the global node number? Again, it's just local DOF indices. Okay. All right, so it's actually pretty straightforward. You'll do that with f, and you'll also do that with k. Of course, k has two indices, so we have two loops here. We have a loop over A and a loop over B. Now, the one thing that you need to be a little that you need to be aware of, really, is that since k is a sparse matrix, we can't just do k. I'm going to say A global just as a shorthand, and B global. You can't just do plus equals like this. And of course, A and B here are the local. All right, you can't do it this way. We instead do k dot add, and it's because it's a sparse matrix, and we're not dealing with all of the, not all of the indices are actually available to us. Okay, so you do this k dot add. You have your A global, B global. So these are the indices. These correspond here. And then this term is the actual value that you're adding. So that would be this here. Okay. So those are equivalent as far as the thinking goes behind it. This is, of course, the actual writing that you will do. Okay. Now this assembly process, it's really just two for loops, just a few lines. It's good for you to understand what is going on here, because you'll be doing this exact same process in all of the remaining homework assignments. It's actually the exact same lines of code. Okay. And so it's good for you to understand what's going on here in this first homework assignment. Now the last function that's called in assemble system is this applied boundary values. Now we're not going to go through all the mechanics that we learned in the lectures of applying the Dirichlet boundary conditions. You remember in the class, if we had k d equals f, right? If we happen to know the boundary conditions, if we had Dirichlet boundary conditions, and say these, if we had Dirichlet boundary conditions in on these two nodes, then what would we do? We would actually remove the corresponding rows and columns of k. We'd also remove the corresponding entries in f, and that would give us a smaller matrix vector system, right? I think we set these as bar, and then these were actually kd and f, or something like that, right? The way DL2 does it a little bit differently, instead of actually deleting these rows, it just modifies the entries in k and modifies the entries in f to give you the correct values of d, or the correct displacement values. Okay, so you can actually go to the you can look into that a little bit more if you'd like to. But the main point is that DL2 will be taking care of the application of Dirichlet boundary conditions, and it actually does it without modifying the size of k, d, or f. Okay, so that's what's happening here. You can see we're inputting boundary values, which is the map that we created earlier that holds the values for the Dirichlet boundary values, k, d, and f. This false has to do with whether or not DL2 is modifying entries in the row only, or if it also modifies entries in the column as well. False means it's only modifying entries in the row. Again, that's not something you need to modify, but it's helpful to see what's happening there. Okay. All right, let's stop that segment here, and in the next segments we'll look at solve and output results, which are really short functions, but then we'll look mostly at calculating the L2 norm of the error.